Hybrid Jobs is a feature within Amazon Braket that provisions and orchestrates quantum and classical resources for you, so you can focus on developing algorithms, not on managing infrastructure. We're currently in the noisy intermediate scale quantum, or NISQ, era of quantum computing. This means that the performance of the quantum hardware we have available is highly prone to noise, which can cause errors that limit the size of problems we can solve. To mitigate these errors takes very particular clever use of classical computing techniques like pre- and post-processing and a lot of the recent breakthroughs we've had in machine learning. These tools help us leverage the strengths of current generation quantum hardware, and this is called hybrid quantum classical computing. So, to understand Braket hybrid jobs, we're going to dive a little ways into what are called variational quantum algorithms. These are algorithms for solving optimization problems that have a well-defined cost function we want to minimize. So, for instance, this could be a vehicle routing problem, like figuring out the fastest way to deliver a bunch of Amazon packages, to pick a totally random example. Or for another type of optimization problem, finding the lowest energy or ground state of a chemical system, which can be used to predict things like whether a chemical reaction will take place, or if a new drug will bind to a cancer-causing protein. In a variational quantum algorithm, we parameterize a quantum circuit for the problem we want to solve. So assign parameters to certain gates in the circuit, and then vary those parameters across multiple iterations. Each time we send our circuit off to a QPU, or quantum processing unit, we evaluate the measurement output and compare that result with the previous one to see if our parameters are currently worse or better than the last iteration. So then, over multiple iterations, ideally you will converge on the optimal set of parameters that find the solution to our problem and minimize the effects of errors in our circuit. If you're familiar with neural networks and machine learning, you might notice that updating the parameters after each iteration is analogous to updating weights in a neural network. And actually, we can take this analogy even further. You might already know that it's very common to use GPUs in training neural networks. And that's because they are hardware optimized for highly parallelizable matrix operations like convolution and multiplication that come up in training neural nets. CPUs, on the other hand, are best suited to sequential processing tasks like loading in data, pre- and post-processing, and updating parameters after each iteration. This happy domestic partnership between GPUs and CPUs is called co-processing. And it's the same model we use to think about hybrid quantum computing, with QPUs taking the place of GPUs. One important difference between GPUs and QPUs is that QPUs have performance that drifts over time and need to be recalibrated regularly. We'll put a pin in that. Now, I haven't said anything yet about how you choose your new parameters after each iteration of your algorithm. And that's because there are actually a lot of methods you could choose. It'll depend on your classical optimization algorithm. And this is where hybrid jobs comes in. You specify which quantum device you want to run on, the type and amount of classical compute you want to use, so a cornucopia of GPUs and QPUs to your heart's delight, which are resources that will be released as soon as your job is done. And not only that, but with hybrid jobs, you get priority access over your chosen QPU, which can help mitigate those errors we mentioned due to drift. So, once you've chosen your classical and quantum compute, you'll write your code and update the parameters of your quantum circuit using your preferred optimization method, like meld or mead, which is my favorite. So now this is all a little abstract, so let's walk through an example to see how it works. Let's say you want to run an algorithm like the variational quantum eigensolver to find the ground state of a particular molecule. You load in the geometry of the molecule, encode a description of the energy of the system, so the Hamiltonian, into a parameterized circuit, and then pick your favorite optimization method. Let's say you know that running VQE on this molecule may take a while to converge, and you're giving a talk at a conference tomorrow, and you're waiting at the airport at 11:30 p.m., trying to get your VQE experiment running before you take off, because it's a tragically no Wi-Fi flight. So you really don't want to worry about your Jupyter notebook crashing after you set it off, or your laptop deciding to auto-update overnight and losing all your progress on your algorithm. So, because you're very clever, you submit the algorithm as a hybrid job on Braket, which will run regardless of the state of your sad laptop. You got 5 minutes until they're going to start boarding your group, so just to be sure, you run a local hybrid job, just using a quantum simulator to make sure there aren't any bugs in the code. Then you can happily send off your hybrid job to Braket, where you'll get priority access over your chosen QPU, and because you were proactive, you remembered to add checkpoints which will save your work in case anything happens to interrupt it. If you want to check back in on the progress of your algorithm, you can go check AWS CloudWatch. And now you can go try to get a few hours of sleep before your invited talk at 10 a.m. So, to summarize, Braket Hybrid Jobs is an orchestration service which handles quantum classical resources to run variational quantum algorithms and gives you priority access to QPUs with no upfront commitments or costs. It's particularly useful for long-running algorithms where it's really important to keep your progress and not be impacted by interruptions on your local machine.
If you're enjoying these videos, please give us a like and consider subscribing to the channel so that we can keep making more to help you understand how the cloud works and to show you new ways to help all the scientists and engineers around you who use HPC every day to do amazing things. It's what gets us motivated as well. See you next time.